Hi folks, Glenn here. Today I wanted to give a brief demonstration and an overview of my latest USB project. It's right here. We'll start off with a quick demonstration, then we'll be back in about 20 seconds to give an overview of how everything's connected together. And following that, we'll do a deep dive into each of the major components of the project. Welcome back. I hope you enjoyed that brief demonstration of my latest USB project. Let's go into an overview of how this is put together. The first component is this push button switch here, and when you push the switch it closes a contact at the back of the switch that pulls a pin on a microcontroller here low. That sends a USB in packet, a USB in report up to the Microsoft Surface here that's running a Windows 10 app. That Windows 10 app takes some parameters off the GUI, sets a bunch of timers, and then sends USB out reports back out the USB cable to the EFM8 UB1 microcontroller, and then the EFM8 UB1 microcontroller turns on and off the LEDs behind the display. So that's kind of an overview of how it works. Let's dig in a little bit deeper on the switch first, and then we'll talk some about the board and how the board's put together, and then we'll get into the Windows 10 app and how it's running on the Surface. Let's start with the push button I chose for this project. This is by far the most mechanically complex push button I've ever seen. At the front is an illumination unit housing some incandescent bulbs that light up the indicator on the front. In the middle is a holding coil that we'll get back to, and at the far end are the actual switches, which are micro switches. So this thing's designed to be relamped from the front of a panel without having to take it out. And the way that's done is you put a finger on each side and you pull it out straight out, and then once it's out all the way, you turn it 90 degrees and then kind of push it back in a bit, and then the lamp unit comes out of the housing. So this is so that you can relamp it without having to take apart whatever it is you're working on. Once it's out, you can push the bulbs out like that, replace the bulb, push it back in. Another thing that's kind of interesting about this are these little white curtains that keep the light from one bulb shining over and illuminating the segment that's not supposed to be there. When this is up inside the switch, it's pressed kind of flat like that, and these little curtains are sufficient to block the light from getting through from, like, say, this bulb over to this segment, or from this, from this bulb to this segment. So the other thing that's interesting about this, and pretty complicated, is how it actually mounts in a panel. It's inserted from the front of the panel. You take this little bracket off, push it through the front of the panel, then once it's in, you push this bracket back up to the back. And if you look closely inside here, see if we can get this in focus and in camera, there's two screws pretty deep inside here, one on this side and one on this side. And once it's in the panel and you have that metal bracket pushed all the way up, when you turn those screws, these little lever things right here, they twist out, and then as you further tighten the screw, they move upwards towards this metal piece, and then they apply a force and keep this from moving in the housing. Let's go ahead and put the indicators back in. They only fit in one way. I think I got it right. There we go. So they're back in. Now let's talk a little bit about the holding coil. This will actually be easier like this. In today's microprocessor-controlled world, it's like you detect a press, and then a button press, and you have some register bit somewhere. It says, oh, that or a variable, and you say that button was pressed. We need to stay it, and we need to keep it pressed and keep that it's on. And then the next time you press it, you turn that bit off, and then the switch is off. This switch is from 1988. I'm sure they had computers and stuff back then. Seems a while ago, but they also needed a mechanical way to keep the switch depressed once the user stopped pressing that. And the way that was done is with this holding coil right here. So if I just press the button normally, the switch presses, releases, and you can hear it click. But if I energize this holding coil, and I'm going to try to do this without making any sparks, all those sparks are kind of fun. All right. Now if I push the switch, it clicks when I press it, but when I release it, it doesn't click. And if I press it some more, it doesn't click either. And the reason that happened is that as long as this holding coil is energized, this plunger right here, right in there, stays pressed in and keeps the switch closed until I de-energize the coil. And then when I de-energize the coil, it pops back out again. If I just energize the coil sitting there, it doesn't have enough force to actually move the plunger and press the switch on its own. So I have to press it again, and then it'll hold until the power is removed again. So that's kind of an interesting feature of the switch that I never really seen before, had much experience with. I'm not using that in this project, but it's there in case I need it for a future project. And if you look closely there, you can see 8803. So this switch is made in the third week of 1988. I'm not sure if that's the part number on there or what. But, so that's how this works. One curious side effect is that, or one curious thing to note on this, is that if we pull the indicators out again, all of the incandescent bulbs, the housing of the bulb shares one contact, which is the ground. And then these replacement LEDs I have, these are the anodes, these 4 contacts. So this is basically common cathode LED matrix, which means I take the cathode, connect that to ground, and then to turn each one of these off, I have to apply a positive voltage to one of these 4 locations. And that's going to be a major driver of the design of the board going forward. Having to basically high side switch the voltage to the LEDs versus being able to just put 24 volts on there and pull a ground low for one of the 4. So with that said, let's move on to the circuit board. All right, here's the circuit board. I have it resting up against the switch, and hopefully it'll stay in focus for the next minute or two here. So this board connects to the switch using, or connects to the LEDs that are in the switch using this 5-pin header here. It connects to the switch contacts themselves using this little 2-pin header, and then it connects to a PC using this USB Type-C 2.0 or USB 2.0 Type-C connector. When you press the switch, it closes a contact on the Silicon Labs EFM8 UB1 microcontroller. The microcontroller is running software that sends a USB in report back to the PC over USB saying, hey, the switch has been pressed. It also sends another one when that switch has been released. Then the PC can send a USB out report to the EFM8 UB1 microcontroller telling it what brightness to set each of those 4 segments at. And the way that's done is using this PCA 9685 PWM controller. It's a 16-channel part, but I'm only using 4 of those channels, and so it uses the I2C bus to set channel 0 to this brightness, set channel 1 to this brightness, channel 2, channel 3, and that controls the brightness of the LEDs on each of the segments here. To actually switch the voltage going to there, I'm using this part that's new to me. It's an Allegro Micro A2982 high side switch. It's basically like some of the ULN, I think they're 5800 series parts, except that it can switch the high side of the circuit. So instead of you apply a voltage and it connects one of its pins to ground and closes the circuit, in this case you apply a voltage and it feeds out, in this case about plus 12 volts out to the light, and then the light comes back in on a common ground. So this is a high side switching device instead of a low side switching device, which they're kind of rare. Looking through DigiKey's catalog, I only found this one, and then I found one from Infineon that was quite a bit more expensive. The other thing that drove the design, besides needing a high side switch, is that the LED replacement bulbs are designed to run off of 24 volts, and the 12 volt bulbs were a 100 part minimum order at about $4.50 a piece, and the 5 volt bulbs are the same thing. And I didn't have $450 to spend on 1 amber, 1 green, or 1 red, 1 green, and 2 amber LED replacement bulbs. So I just bought, so I ended up having to buy 24 volt bulbs, which I could get, quantity 1. And the good news is the 24 volt bulbs will run from 12 volts. The bad news is that USB only has 5 volts. So I found this 5 volt to 12 volt DC converter that'll take 5 volts and convert it to 12 volts with a budget of about 250 milliamps. total. These 4 LEDs use about 60 milliamps, so I'm well within the constraints there. But you can't just hook the 5-volt input of this up to the USB thing, because you will exceed, because this boost converter requires a 22 microfarad capacitor, which is right around there. And if you do, that 22 microfarad capacitor will get placed across the 5-volt power rail of the USB bus. And once that happens, the 5-volt power on your 5-volt power rail in that USB port could dip below 5 volts and affect other devices in the system, or throw one of the PTC resettable fuses and shut down the port. So you can't actually apply that 22 microfarads of capacitance across the bus when you immediately plug this in. So there's a little tiny switch IC right here. This AP280, it's like a 5-pin SOT23. And what that does is it has a very slow ramp time, and it also has an enable pin. So when you plug this into the USB port, that microcontroller as well as a pull-down resistor keep that switch turned off, which keeps 5 volts from flowing into that capacitor, and also keeps the switching regulator from turning on. After about 100 milliseconds of being powered on, the EFM8 UB1 will turn on that switch, and that switch has it has a current limit on it. So it takes actually about 800 microseconds for that 22 microfarad capacitor to charge up to 5 volts, and that keeps us well within the specs on the USB bus, for max capacitance and the most we can as fast as we can pull voltage current from that power rail. So that's kind of that board. There's the the USB 2.0 Type-C connector. There's some the miscellaneous parts. There's some ESD protection, some capacitors that are required for the EFM8 UB1, a decoupling cap for the PCA 9685, a little push button to put the EFM8 into bootload mode, and then the stuff required for the boost converter. That's the board. Let's go on next to the Windows 10 app. Okay, I turned down the lights a little bit so we'll be able to see the segments on the indicator light up a little bit better. But let's move on to talking a little bit about the Windows 10 app. This is basically a C#, it's just a basic C# .NET Windows Form app. And right now it has a couple of different test modes. One thing you want to do is you want to be able to make sure that you're able to control the LEDs. So it's got buttons you can click to turn each of the 4 LEDs on and off independently. The testing strip is actually made up of 2, so you turn 2 on and turn 2 off. The other thing this thing does is it lets you set the number of times the testing light blinks before it gives a result, and then you can pick the result you want. So I just set it up for 3 blinks, and it's always going to return and go. So now if I push the button, testing blinks 3 times and it says go, or I can click no go, push the button again, 3 blinks, and it says no go. Or we can pick a random result and say, let's do 7 blinks. So now if I push the button again, testing blinks 7 times, and there's no go. So that's kind of just a really basic Windows Form app to give a little demonstration and test the hardware out. I think you could do things too, like you push the testing button and you'd have an application running on the PC that would kick off another application, like say compile of some code or something, and then when the compile came back, it could either illuminate the go or no go light based on whether the compiler was successful or not. Or if you have a test bench you wanted to run, you'd hit the button, it'd run the test bench, then come back with either a green light or red light based on whether or not it worked. I hope you enjoyed this demonstration of my latest USB project. If you want more details on this project or any of my other USB gadgets, be sure to check out my website at bikerglenn.com, and we'll see everybody next time.